All right, chemistry class, this is Coach Jeans, and in today's video podcast, we're going to start Unit 4. Unit 4 is titled The Mole, and the mole is something that we're going to use a lot in chemistry, so it's a good idea to make sure you get this concept now. It will help you out throughout the rest of the year. So you should be in your composition notebook. You should have a new unit. You should already have completed the outline and completed all the stuff that I wanted you to put on your odd pages. So on your even pages, you want to follow along with me and add your notes. Well, first of all, what are we talking about when we talk about a mole? It's not this kind of mole. It's not this furry little animal that lives most of its life underground and is virtually blind and burrows holes and makes problems for golf courses and things like that. Nor is it the other kind of mole. It's not the little mole that's on a person's skin. It's spelled the same way, but it is something different. So what is the mole in chemistry? Well, first of all, why was this created? The mole in chemistry was created to make very small things seem much larger. Things like atoms and ions and molecules. Those are the typical things that we're dealing with in chemistry, things that are microscopic and on the atomic level. And so we have to take those things and we have to try to deal with them, and it helps if we make them seem larger. It also helps us count out these very small atoms, ions, and molecules. Again, since they're very small, we need some sort of a unit that'll be convenient to be able to count those out. So that's why the mole was created. What is it like? Well, first of all, it's sort of like a dozen. We know that a dozen is 12. So if we have 12 eggs, we've got a dozen. If we have a dozen roses, we've got 12 roses. A dozen of anything is 12. Doesn't matter what those things are. If we say we have a dozen of those things, we know we have 12 of those things. Or maybe it's like a ream of paper. If you have a pack of copy paper, you go to the store. You're not going to buy it by the sheet. You're going to buy it by the pack. And a lot of times it'll come in packages of 500, and that's called a ream. So a ream of anything is 500 things. Or maybe it's like a gross. A gross is 12 dozen. And 12 times 12 is 144 things. So the mole is just like these things that we've used in everyday life, but it's now dealing with something that we're going to use to count very small things like atoms and ions and molecules, etc. So the mole is a much larger number than a dozen or even a ream. The mole is equal to this number, 6.02 times 10 to the 23rd, whatever, things, okay? So if you have a mole of things, you have 6.02 times 10 to the 23rd. So what you'd have to do is you'd have to take 6.02, you'd have to move the decimal place to the right 23 times. So that's basically 602 with 21 zeros on it. It's an extremely large number. It's almost mind-blowing, and it's hard to comprehend that big of a number. When we're trying to get a grasp at how many things that is, a mole of things that is, if you think about M&Ms, if you had one mole of M&Ms, then it would cover the entire continental United States. That would be from East Coast to West Coast. That would be from the northern border to the southern border of the 48 continental United States. But the depth of that would be 125 kilometers, which is about 77.6, 77.7 miles deep. So think about how deep that really is. Okay, that is a tremendous amount of M&Ms, and you would just have one mole of those things. So it's a really, really big number. Why so big? Again, atoms, ions, and molecules are extremely small. All right, so again, a mole is like a dozen. It's we count dozens, it's 12 things, 12 roses, for example. Or it's like if we have 500 things, we call that a ream. If we have 144 things, like in boxes of pencils, all right, we have a gross. And then if we have 6.02 times 10 to the 23rd things, we say that's a mole of things, okay? Now, it's also known as Avogadro's number, and it's symbolized by a capital N sub A to stand for Avogadro's number. It's named in honor and in memory of Avogadro. Amadeo Avogadro was a scientist, and he's the guy who first worked with this quantity. He published his work, and many of his contemporaries, his other scientists, did not agree with him, and they basically just rejected his findings. Sadly to say, he died, and then a few years later, the scientists came around and they looked at his work again. They said, wait a minute, Amadeo was right. And so they went back and they named that number 6.02 times 10 to the 23rd Avogadro's number in honor and memory of him. So it's kind of a sad story that he died probably thinking he was a failure, but he wasn't. Here's another illustration to try to get a grasp of how big 1 mole of things is. If you had 1 mole of rice, regular uncooked like white rice or whatever, then that would fill up a cube, and that cube would be 120 miles on each side. So think about a really, really big box. That's 120 miles long, 120 miles high, and 120 miles deep. That would be 1 mole of rice, an extremely, extremely large number. All right, now, why is it so big? Again, atoms are extremely small. If you took carbon atoms, for example, 1 mole of carbon atoms would be able to fit in the palm of your hand. It would be about what you could fit in a teaspoon. And you could fit that in the palm of your hand, or your palm of your hand. So carbon is basically, it's graphite. Same thing if you're writing with a pencil. That's what carbon is. And so if you grind that up and put it into a powder type form, you could put 1 mole, 6.02 times 10 to the 23rd atoms of carbon into the palm of your hand. How could you fit that many in the palm of your hand? Again, atoms are extremely, extremely small. All right, so go to page 3 now in your composition notebook, and page 3 or 4, you want to add notes here. We have here what's called the molar mass. What we need to be able to do, we can't count 6.02 times 10 to the 23rd things. Even if you started counting right now, you would die way before you got even near the end or even got up to that big of a number of things. So what we have to do is come up with a convenient way of counting very small things. And we do that by using the mass. This is very similar to what if you go to like an old-fashioned style candy store and you're buying something like gummy bears or something like that. They're going to sell it to you by the pound. They're going to weigh it out and sell it to you. And they know, give or take a few, how many gummy bears are in a pound of gummy bears. Very similar here. We're going to use mass, and the mass that we're going to use is called the molar mass. Basically, it's defined as the mass of 6.02 times 10 to the 23rd particles of a chemical. It's also equal to the sum of the atomic masses of a chemical. So if you don't have your periodic table handy, pause the video right here and grab your periodic table. All right, with your periodic table in front of you now, find the element carbon, for example. All right, when you look at the element carbon, you've got the number above carbon, 6. That's the atomic number. Then you have the number underneath carbon, and it's like 12.01. Maybe it's 12.011, depending on what periodic table you're looking at. But that is called the atomic mass. Well, that is equal to the molar mass of carbon. And we express this in grams per mole. So you change, normally atomic mass is AMU. So you change it over to grams per mole. So carbon would be 12.01 grams per mole. Now find iron on your periodic table. Iron's right in the middle, okay? Well, the atomic mass for iron is 55.85. So if you round that off. So 55.85, if you had that many grams of iron, then you would have 1 mole of iron. You would have 6.02 times 10 to the 23rd atoms of iron. So 1 mole of carbon has a mass of 12.01 grams. 1 mole of iron has 55.85. So you might say, well, if they're both 1 mole, why is their mass different? Well, think about it like this. Let's suppose you had a dozen roses and a dozen bricks. Which one's going to weigh more? Obviously, it's the bricks, right? Because 1 brick is a lot heavier than 1 rose. So if you have 12 bricks, it's going to be heavier than 12 roses. It's the same thing with atoms. If you have 1 mole, that's 6.02 times 10 to the 23rd atoms of carbon, it's going to weigh 12.01 grams. But if you have that same number, 1 mole of iron, then it's going to weigh 55.85. And again, the unit here is grams per mole. So the way that we do this, what I need for you to do right now is pause the video right here, and I want you to jot down this periodic table, and we're going to work some of these out in class. You'll also, right now in the video. And also, you're going to need that periodic table handy. You're going to need your calculator in order to work these out. Okay, so after the pausing the video, let's flip over a little bit here, and let's work on some of these right now. Okay, so you've got this chart copied down into your notebook, and we're just going to work them out right here. So the first one is iron 2 hydroxide. All right, iron 2 hydroxide. Now, you're given the name of the chemical, before you can do the molar mass, what you have to do is convert that over to the formula. So we do this the way we've done in the past. We have iron, Roman numeral 2 gives me a 2 plus. Hydroxide, remember that's a polyion. If you don't know, look it up. It's OH, 1 negative. So we need to make sure that we write the formula as FeOH2. Now, if you need help with this, make sure that you go back and look at the videos, or you get help from me in class or from your teacher, and make sure you can write the correct chemical formula. Now, from the formula, we're going to figure out the molar mass. So we first look up the first element, which is iron. And it says show your work, so we're going to put 55.85. Now, we need to multiply that by the number of irons that are represented in the formula. There's only one iron represented, so we're going to say times 1. Well, that's easy. That's 55.85. Now we're going to go to oxygen. We look on the periodic table. We find that the mass of oxygen is 16.00. Again, I'm rounding it off to 2 decimal places, and that might be a little different on your periodic table, but if you round it to 2 decimal places, that's what it is. And it's going to be multiplied by the number of oxygens that's represented. Now, remember, you got parentheses. So the 2 on the outside of the parentheses distributes, it multiplies by everything on the inside. So that 2 times 1 gives you 2 oxygens. So we're going to multiply that by 2, and that equals to 32.00. Now we're going to do hydrogen. We look it up. It's 1.01. And again, 2 times 1 is 2, so we multiply that, and we get 2.02 right there, okay? So then we're going to add this up, and let's say we got 9, and we've got 89.87. And what's going to be the unit? Grams per mole. So this would be your final answer there. All right, let's take a look at the next one. We have aluminum sulfate. Okay, so aluminum sulfate. All right, first thing we have to do is write the correct formula. Aluminum is Al, it's a 3 plus charge. Sulfate, SO4, 2 negative. So we need Al2, SO4, and we need parentheses with a 3 on the outside. All right, then we go to our periodic table. We look it up. We have aluminum is 26.98. We're going to multiply that by 2 because that's the number in the formula. We're going to have sulfur. It is 32.07. And we're going to multiply that by 3 because the 3 distributes. Okay. And then we have oxygen is 16.00. Now we have 4 on the inside times 3. So 3 times 4 gives me 12 oxygens. So then we take our calculator and clear it out. And then we're going to go 26.98 times 2. And that gives us 53.96. 32.07 times 3. And we have 96.21. And then 16 times 12. And that's 192. All right, now what we need to do is we need to add all that up. All right, so 192 plus 96.21 plus 53.96, and that equals to 342. And we'll go ahead and go to 2 decimal places. You could round out off the 342, give you 3 significant figures, but I like to just go to 2 decimal places. It makes things more convenient for my students. So, and then again, grams per mole is the unit that you want to make sure you have with each one of these. All right, the next one is sodium hydrogen carbonate, or it might say sodium bicarbonate. That's the same thing. So sodium hydrogen carbonate is the compound. Okay. So sodium is Na, and hydrogen carbonate, also called bicarbonate, is HCO3. Sodium is a +1. Bicarbonate is a -1. So we have NaHCO3. All right, now we're going to go to our periodic table. We're going to find sodium over on the left. It's 22.99. Okay, times 1. So that's 22.99. And then we're going to go hydrogen, 1.01 times 1. Okay. Then we're going to go carbon, 12.01 times 1. And again, all these numbers come from your periodic table. We're going to go oxygen, 6.00 times 3. Okay, so that equals to 48. All right, now we need to go back and we need to add all that up together, all right? So we have 48 plus 12.01 plus 1.01 plus 22.99. All right, and equals and 84.01 grams per mole. All right, let's do another one. Let's do dinitrogen pentoxide. All right, so this one is a molecular formula. Here we go. Let me get it where you can see it. Dinitrogen pentoxide is a molecular formula. So we have nitrogen, di means 2. We have oxygen, penta means 5. All right, we go to our periodic table. Nitrogen is 14.01 times 2. Oxygen 16.00 times 5. All right. So that's going to be what? 28.02, and 16 times 5 is 80. All right. And so we're going to add that up, and we're going to get 108.02 grams per mole. And so that's how you do the molar mass. So each different compound has a different mass for each of the unit, or for each of the chemicals, the compounds that you would want to have. All right, there's one more slide that I want to make sure that you get before we stop this video, and this would be on page 5. And we want to talk about what is the volume of a mole of a gas, what we call the molar volume. Well, 1 mole of gas takes up the same amount of space no matter what. It's 22.4 liters per mole. So we write it as 22.4 capital L / MOL. Now, I said no matter what, but really this has to be at standard temperature and pressure. We say STP. It means standard temperature and pressure. And the value of standard temperature is 0 degrees Celsius, which is also equal to 273 kelvins. The value of standard pressure is 1 atmosphere, which is also equal to 101.3 kPa. That stands for kilopascals. And so if you have a gas and it's at this temperature and pressure, no matter what the gas is, it could be oxygen, gas, carbon dioxide gas, helium, no matter what the gas is, if it's at that temperature and pressure, then the volume will always be the same, 22.4 liters per mole of that gas. And so you want to keep that in mind as we do these types of problems. In the next video, we'll look at some mole conversions, and I'll show you how we can use this to convert from different units with the mole. Well, until next time, hope you have a good day. Look forward to seeing you in class, and enjoy studying some chemistry.